Snell's law, right, or laws of reflection. So, which is also true for random surfaces as well. But of course, if you have very complicated random surfaces, it's very hard to do Snell's law, right? If you have very, very complicated structures. So you want to have a simpler approach to address these things, which is the whole purpose of that paper. And that's why I want you to understand it well enough. So let's go through some very basic things with some examples. Okay. So we'll look at a very simple example here. Okay. Imagine a piece of plastic. Okay, it can be solid, but let's say imagine a piece of plexiglass. And it's kind of rough on both surfaces. Okay, its refractive index is n. And let's imagine this piece of plexiglass is sitting in baked in blackbody radiation. Let's say it's sitting in space, baked in sunlight. Okay, so it's basically blackbody radiation. Now, under thermal equilibrium, of course, this will reach some temperature related to what the blackbody radiation is. Right? Eventually, it will heat up and then eventually reach a temperature. So, under thermal equilibrium, we can calculate what's called the electromagnetic energy density by the Planck's formula. So, this is something we saw in one of our early lectures. Of course, you don't need to remember, but the idea is to relate one particular property, which I'll come to in a second. So, electromagnetic energy density essentially refers to the fact that if you take any point inside this material and look at how much energy is there per unit volume at any location in the material, you can calculate that. There is energy because there's photons bouncing around, right? There's light inside. We all know from geometrical optics that light from outside will refract in, right? So we know there's light here, if there's light, there's photons, if there's photons, there's energy. So this equation tells us what is the density of energy at any location inside this material. So it's simply, h bar omega, h bar is a constant, let's ignore it. Omega is the frequency. We know that the energy of a photon goes as h nu, right? hc over energy of a photon is h nu, and u times lambda is c, and omega is 2 pi nu, right? So it's something like h omega over 2 pi, or just h bar over omega. So in other words, the energy of a photon is h bar omega. Right? So that's where that comes from. Divided by, this comes from what's called a Newton partition theorem. These things are not so important for us. But the important thing to remember is it depends on temperature. So h bar omega 15 minus 1. And then there's all this stuff. Again, mostly they're all constants, except for k. K is the wave vector. So d omega is simply the solid angle. So we're looking at this one solid angle. Actually, no, sorry, that's the volume. So it's small volume. Not important for our discussion here. K is important. K squared d k over vector. Now k is the wave vector n omega over c. Now k, we've seen this before. Just to remind ourselves. K is also called a wave vector. It's 2 pi over lambda, inversely proportional to lambda. It's also called a wave vector. Okay. Now, what's interesting, of course, is the n. Okay. So this depends on the material. Now, it can be shown. We won't go into the details. But the intensity. So that's the energy density inside the material. The intensity is what you can measure, right? So if you stick a power meter there, you can measure power. Power divided by area will give you intensity. The intensity is given by this energy density multiplied by something called a group velocity, which if you have taken electromagnetic waves, it's simply the velocity of a wave packet of light. Okay, for those of you who are mechanical engineers, think about it as the velocity of a wave packet as a solution of your Hamiltonians. For those of you who have done Hamiltonian mechanics or something, it might relate to that. There's some interesting analogies. In any case, what's important if you plug in all that stuff is this factor here. Let's ignore everything else except that. What we see here is that the intensity inside this piece of plastic, okay, then squared times the intensity outside it. Okay? because everything else is the same outside, right? It's just that n equals 1. It's vacuum. Okay? So again, let me repeat that. It's an important conclusion. The intensity inside this piece of plastic is n squared times the intensity outside. We have done nothing to it except just roughening it just because we'll come to why that's important. But just by putting it in a blackbody radiation, you increase the intensity. Right? It's like magic. It's weird, right, in a sense. But that's what we're going to take advantage of. Now, we're going to make some interesting assumptions in this lecture today. The most important thing is something called an ergodic assumption. We'll assume that the behavior of light rays is ergodic, which refers to the fact that the light essentially behaves in a random fashion once it passes through random surfaces. Okay? So just to read it, this means that once the ray enters a medium which has some random texture on it, it will forget where and in which direction it came from. Of course, the light ray is determined by angle and position. Right? We know this from geometric light. What ergodic assumption means that once it passes through some random texture, it will forget its history. It will forget where it came from, forgets its direction. Okay? So this creates what's called statistical randomness. And this is our assumption we're going to make. Now this, we're going to spend a little bit of time understanding what this means next. Actually, not next, before we go ahead, let's just reiterate this. It's the same thing as I said before. The intensity within a medium in thermal equilibrium with a blackbody radiation is n squared times higher than its environment, which is what we said. So notation-wise, the intensity in the interior, okay, that's what that INT means, the function of omega and x is the position, omega is the frequency, is n squared times the intensity in the exterior. And this BB refers to a blackbody. And of course, in the exterior, there's no x. It's uniform. So you only have a function of omega. Now, this also means that this material can also vary with x. In other words, you can have an inhomogeneous material. It's not so important for us for now. We'll come to inhomogeneous materials when we talk about anti-reflection theory. But that's a different discussion. So what happens in the case of the ergodic behavior of light? So again, let's look at exactly what we're talking about. So again, we have a textured surface, a random texture. Let's imagine direct sunlight comes in, like pollinated light. Simple to understand. It will refract here in, right, Snell's law, with some angle. And then it can, part of it can reflect, part of it can refract out. Right? It depends, of course, on critical angle and so on. We all know this. Let's imagine part of it is reflected, and then it's reflected again, let's say. Okay? Now, what happens is that if you have a little bit of randomness on these two surfaces, the light can get randomized in terms of its position and direction very, very, very quickly. It will reach this ergodic state. And we can prove this actually. And this does not have to be blackbody radiation. It can just be anything. Just a non-black body. So we can show that this is true as long as the rays are ergodic. That is, they forget their initial direction after one or two reflections, statistically average over the area. So the three things that are important when we talk about this random nature of light. One is the fact that it can randomize because of the location where it hits. Right? Because it's where it hits determines the refraction angle, and every location is a little bit randomly different. That's one. Second thing is that upon the second reflection, also the same kind of situation can happen because the angles here are also random. Right? So where it hits, it can randomize a bit more. And keep going. So you can have more. The third thing that's important is that when we talk about statistical optics, we always have to average over some area. You don't think about a single ray. Okay? You don't think about a single ray. You have to average over a bunch of rays over some area. So when you average over an area, where there's this randomness on this texture, you can imagine all these rays, once it enters the medium, will become fairly random, kind of mixed up. Of course, this is a very qualitative explanation, obviously, but you can actually mathematically prove this as well. And there's more, I would say, more rigorous explanations in the paper. For us, this is enough. So we're going to introduce one other thing. Light comes in. We're going to introduce a white reflective surface in the back. And this turns out to be very common in solar cells. We'll see this again and again. And the main reason for this is that you want any light that escapes the system to go back into the system. So you get twice the pass, 2 times the passes. And in this situation, like it's an additional pass, and what happens is you get an additional factor 2. So the intensity in the interior is now 2n squared intensity incident in this case, outside. Of course, this reflective surface can be this surface as well, right? They can be combined. You can imagine. This is exactly what happens in very nicely designed solar cells. Because actually, before I do that, because first of all, we should understand what are we trying to do, right? Why are we looking at this? So imagine this is a solar material, solar cell material. Yeah? Well, we are trying to absorb the light. Right? Now, the more times light passes through it, the more chances of it being absorbed. That's why we are trying to make it go through many, many times. Okay? I forgot to mention that. So that's the big picture. We'll see this again. We have a whole lecture on light trapping later on. So a few caveats to think about before we proceed. One, this discussion so far is only true for optically thick films. So in other words, this thickness here has to be larger than lambda over 2n. This is a technical detail, not important for us. It has to do with the fact that geometrical optics breaks down if you go to very small dimensions. Right? We need to apply diffraction and solve Maxwell's equations and things like that. We won't deal with that for now. Okay? So it has to be somewhat thick. Technically, it has to be about lambda over 2n, and being refractive of the material. And the second thing is that we have ignored absorption so far. We will introduce absorption because we are trying to absorb light. Right? So just not having absorption is meaningless at the moment. But let's do a quick analysis here. Now I want you to spend 15 seconds or so answering these 2 questions. First of all, let's imagine a wavelength of 1 micron, easy number, and let's imagine silicon. The refractive index is 3.5. Now, silicon is actually transparent or close to transparent at 1 micron. Okay? So it's like glass. Although if you look through silicon, obviously it's opaque. So what is the smallest thickness our theory is valid? Easy. So very quickly. The reason is just so we get some scales, right? So 1 micron is 1,000 nanometers. Now, I said lambda over 2n. I'm going to say 1,000 nanometers. I'm sorry. 1,000 by 7. So what's this? 1, it's 30, so it's 4. This is 2. So that I'm which is quite very, very big. So this means that what we're going to talk about is valid for almost all solar cells that will be of interest, because all solar cells are definitely more than a micron thick, for example. At least there are some examples. Okay, second question. How much enhancement in intensity is possible? Now, enhancement intensity is very important to understand because that's what we're going to use to do the absorption. So, is it an opportunity? Yeah, it's just, but I want to do the calculation, tell me, because we want to appreciate how much we can enhance it. Yeah, it's something like that. So 2n squared, 2 times 2.5 squared. 2 times 9, right? So let's say that one. Is there more than 2? Yeah, 24. So this is a big deal, right? Imagine if you could increase the absorption of the solar cell by a factor of 20, a fact, an order of magnitude. That's huge. Right? It's a big, big deal. Of course, it's hard to get the theoretical limits. Huh?
The theoretical randomness?
No, the randomness is the easy part. It's hard to get the theoretical absorption limit. So let's do n squared enhancement. This is the intensity enhancement, of course, right? As we will see, there are loss mechanisms we have to address, which we have in optical. We will talk about it soon. But we'll come to the actual enhancement of efficiency or current. No, that's one way to look at it. So, but a few points about ergodic behavior. So, first of all, let's think about what an ergodic behavior means. Let's look at very symmetric cases, right? Let's imagine a billiard table. If you have a billiard table, let's imagine, so in this case it's 1 times 2, so that's just the aspect ratio. So it's a rectangle. So if you send a ball in one angle, it has one angle that it can access. Right? It can bounce, but you can only get one angle. And the number of angles you can access is always limited because of the high symmetry to two discrete angles, independent of what this rectangle is. The number of passes you can compute that number, and then the aspect ratio. It's not so important, but you can see at most you can only get 2 angles, whatever you do. Okay? So imagine light in a billiard darkness situation. So the high symmetry in this rectangular shape prevents you from randomizing the angles. Of course, the light is very different than billiard balls, primarily because you can have escape, right? Light can escape. It's not a perfect reflector that this film here, even if you randomize it, if it can come in, it can also go out. Right? So it's not a fully exact analogy. So the conclusion, the qualitative conclusion we can draw, is that the more that you can include, if you can make it a polygon on the table, ergodic behavior can happen very, very, very quickly. So of course, rectangle is a second step, right? Before rectangle comes a circle. So you can imagine what happens if you have a circle and you send light through one of the radii. It's highly symmetric, right? It's no angle. Goes like through. So if you send it another angle, you can maybe get some effect. But you can calculate the number of angles you can access. It's still quite limited. However, if you can make more shapes here, you can make the statistically random behavior happen very quickly. So the other thing is that systems are not closed because light can escape because of critical angle. This we will come to in a second here. Here, the reason light is trapped here, because we're talking about if you ignore the reflector, it has to do with the fact the critical angle. Right? So only what's beyond the critical angle will get reflected back into the film. What's inside the critical angle cone will escape. So we need to compute what that is. Right? And that's, of course, different from a ball. So that's what's analyzed here. And this, I don't remember if you had a question related to this in the midterm, but it's something you should be able to analyze. So let's imagine a point source of light. It's embedded in some semiconductor, higher refractive index than another outside. So if you can have light going in all directions, right? So some of the light comes here at a very steep angle, larger than the critical angle, it's totally internally reflected. Some of the angles at a shallow angle within this, what we call the air cone, so less than the critical angle, will refract out. Same thing happens over here, right? Of course, here, because the refractive index of this substrate may be it's a little bit higher than that of air, this escape cone is larger. Right? It's N1 over N2. So let's do a quick example. Can you, I don't have it on the slide, but let's do it here. so we can appreciate this better. N2, N1, N1. So tell me what the critical angle here is and what the critical angle here is. We're going to ignore what's underneath. This is infinity. And then we're going to say N2 is greater than N1 greater than N2 greater than 1. So what's this? And what's this? So the first one is on this line, so you just look up. Yes, so it's just reverse sign of 1 over N1. What's this? Right. N1 is larger than N2, so it has to be the other way. Otherwise, it will be larger than 1. Now, it's an important question. If this is smaller than this, what happens? You don't have a critical angle. You just go. There is no total angle. Total angle deflection only happens with high refractive index to low refractive index. Right? You should know this. So, what is the conclusion? Which one's larger? Because I should give some numbers, but make some guess. Right? Right. Is that clear? And 2 is greater than 1, so I have to draw this. The size is larger. Right. So the probability that the light will escape the bottom is higher than the probability it will escape to the top. Okay. Now imagine, I'll ask you a slightly unrelated question. Imagine this is an LED. Yeah, you have the answer. But is this good or bad? I mean, what does this mean? You don't say this. Okay, if it's an LED, what are you trying to do?
The light out.
You want to get the light out, right? It's inside the material. There's nothing you can do. You want to illuminate the room. So is this good or bad? Or not so good. You know, it's going down. It's going down, but you can't see it. What would you do? That's one good idea. Anything else? That's the same as what he said. That's very good. So first of all, let's appreciate that answer first. What he's suggesting is to put a mirror there. So you get light out as much as. Anything else?
Just flip your whole system.
Yeah, you could shape it. Yeah. But how you mean to prevent reduce the. That doesn't solve this problem. Yeah. Now I'm talking about this specific problem. That is useful for other things. But anything else? Well, what's the most obvious thing? I mean, the mirror is kind of non-obvious in my opinion. But what's the most obvious thing?
Make it smaller.
Yes. Yeah, and, you could do it. You would pick a different substrate. But of course, there's nothing whose refractive index is less than 1. Or even equal to 1. Right? 1 is the refractive index in there. There's nothing which is 1 or less. Yeah, that's a fundamental problem, but otherwise that's what I would do. And by the way, the reason 1 is the smallest refractive index you can get, not technically, but in a natural material, is because the speed of light is highest in air, right? Cannot increase. A little bit different. That's the air and vacuum are roughly the same. You can really go faster than speed of light, unless in very specific situations. But anyway, so coming back to this, so I want you to appreciate that. And coming back to this, what we are talking about is the trapping the light inside. Right? So the first thing we want to understand is that we are looking at loss mechanisms, which is related to what your question was. So one of the loss mechanisms is escape. Right? So we need to understand what is the probability of escape. And to understand this probability of escape, we have to compute the solid angles attended by the escape cone. So you have this cone of angles. If the ray comes inside it, it's gone. So we need to find out, okay, what is that cone related to everything else, right? That will give us a probability that the light will escape. So, of course, because it's a 3D thing, we have to do a solid angle. So this is only a 2D angle. So the 3D angle or solid angle becomes 1 over 2n squared times 2 pi. I'm not going to do that. It's not important, but I have some links on the website. You guys can easily work this geometry. So, but important for us is that this number is quite small usually, right? Remember 2n squared was 24 or something we just calculated, right? And 4 pi is what, 12 or so, right? 13. So that solid angle is pretty small. 1/24th of the full sphere. Right? So the higher the index we can get, we can reduce that. Obviously, reducing that is the code. The probability that the light ray inside the medium will escape is small, assuming that the refractive index is high enough. Another way to think about it, a small amount of randomness is required to create ergodic behavior. Why? Because this, one more. This is much more likely to happen as opposed to escaping. Right? That's what we just did. Exactly. Okay. So coming back to our analysis here. Now we can start putting some numbers or some equations. Pretty simple equation. So let I incident be the intensity of light incident on the area element dA. So we're going to look at a small area here of that surface coming from outside, so the light's coming down. Okay, that's the normal to the surface. And it will refract in. So that's the intensity inside, interior, the INT. That's P is the incident angle. Theta is the refracted angle. Theta C is the critical angle. So that's what we call the loss cone. The fraction of the light, let's call it T incident. The function of T, which is the incident angle here, will be transmitted. Right? Will be refracted in. Of course, we also have Fresnel reflections, which you saw in the lecture on geometric objects. Some of the light will get reflected at the interface between two different materials, like air to glass, air to plastic. So it's a little bit of light will get reflected, some of it will get transmitted, so that's the transmission efficiency. Now, the transmitted light must be balanced by the light that escapes, which we call thermal equilibrium. So we're talking about everything has all the transient behavior has died down, so it's under thermal equilibrium with the surroundings. Right? So thermal equilibrium. This principle is also called detailed balance. And we'll see this again when we talk about physics of solar cells. So it's a very important idea, but very simple idea. In other words, energy entering the system must equal the energy exiting the system. If it doesn't equal, that means the body is heating up or cooling down. Right? If it's in thermal equilibrium, it has to equal. It's the same argument we did in the last few lectures as well. So now we're going to do some simple assumptions. So to compute the internal intensity, we're going to first assume it's isotropic. In other words, inside this material, there are no hot spots. Everything is uniform. Just a simplifying assumption. I think it's a reasonable assumption. And then we can compute the interior intensity as this integral of something here, b, int, times cos theta d omega. This is integrating over solid angle. Okay, so we're standing at a position here. We're computing what is the intensity looking in all directions. Because remember, we have angle-dependent intensity here. So this B in int represents the internal intensity per unit solid angle. Okay, why is there angular dependence? Because we don't know what the angles, right? They're all varying. They're statistically random. Right? That's why we have to assume that there could be some angular dependence. we'll remove that thing. And then we can add a factor of 2 by putting a reflective back surface here. We're going to look at the situation where there is a mirror at the bottom. So you get 2 pass. You get a factor of 2. And then you can turn the solid angle into a 2-dimensional angle. So d omega becomes sine theta d theta times 2 pi. And then this integral becomes, instead of 0 to 4 pi in radians, becomes 0 to 90 degrees in theta. Not so important, just solid angle geometry. Again, there are links on the website if you're really interested in working this out for your project or something, or you can ask. Okay, so what, and then what we can conclude is if we take this B int is a constant. Let's imagine it doesn't depend on angle. If it's completely random, it wouldn't depend on angle. Then you can take this out of the equation integral here. And that integral is very easy to do. All you get is 1, half actually. Right? 0 to 90 degrees of cos theta, sin theta. Cos theta, sin theta is, well, we all know, we should also all know this, right? Is sine 2 theta over 2. And then you integrate from 0 to 90 degrees, you'll get a half. Okay, so that removes that 2, and you get 2 pi times b. So simple equation. Now, so that's what's coming in, right? Now, that's what's inside. Now let's compute what escapes. The intensity of light that escapes, it's called I escape, is exactly the same equation, except that you don't have that extra factor 2 because there's nothing coming back. You're not getting that reflector on the top, right? So they're only looking at light escaping to the top. There's nothing going down because you have a reflector there. So same equation, 2 pi, then same integral. Of course, in this case, you have the intensity interior divided by 2 pi, because that's now gives you B interior. Right? This thing is just that. Times this probability of escape, which will be related to the cone angle. So we'll come to that. That's the percentage. Everything else is the same. When you do the integral, you get this simple expression. The intensity of light that escapes is the intensity inside the material times the probability of escape divided by 2n squared. Now, this 2n squared will come from the cone angle. I didn't quite explain that. So this 2n squared comes out because this is theta c, right? When you do this loss integral, we are looking at the top. We have to do the integral from 0 to theta c. Right? You don't need to worry about anything larger. So that integral is how you get, and the fact that theta c is an inverse of 1 over n, we leave it right. This is just a probability. Angular average escape transmission. So this is related to the same thing as the Fresnel reflection coefficient, because you can also have a situation where some of the light reflects and some of the light reflects. What I mean is, we talk about if a ray of light comes here, the probability some light will go out, some light will come in. Right? Even if it's within the spectrum, and some because of the so that's kind of addresses that. But these things we will cancel out, so it's not too important. Now we apply detailed balance. Light in equals light out. So the input is the incident intensity multiplied by the transmission efficiency, as we said before, because we have Fresnel reflection. And the output is the interior intensity multiplied by the, again, the probability of escape, which is the Fresnel reflection. So we can now rearrange this equation and come up with a factor. This equation where the interior intensity is 2n squared times this guy. Now, if we look at this expression, we can make a few assumptions, right? First of all, let's assume that the Fresnel reflections in both directions are roughly the same. Not always true, but let's just assume. Then this stuff cancels out. Okay? Then we get a very simple expression we saw before. The interior intensity is simply 2n squared times the incident intensity. Exactly the same thing we just talked about at the very, very beginning. Okay? So that's fine, that's good, because we have derived, we kind of made some logical arguments, and here we kind of mathematically approximately derived it. But more interesting thing is this factor now tells me that potentially I can go more than 2n squared. Right? Potentially. This factor suggests that one can exceed the 2n squared. For black bodies, this is always one. And it turns out you can exceed this. And if you want to exceed this, you have to take advantage of this factor phi here. So in some angles, you can have a very high or very high incident probability intensity, very low escape probability. Okay. You can imagine doing this, for instance, with the CPC. Right? The CPC does this. Right? By restricting the angles you can get, you're also collecting. In that cone, nothing escapes. Right? Think about that situation. It's abstract because I'm thinking about from a system level point of view. But this can happen if you're willing to restrict the acceptance angle. And it's equivalent to what we talked about in CPC. Not exactly equivalent, but it's analogous. It's also important, but you can think about what I said. The brightness theorem still applies. Not so important for us because we didn't really talk about the brightness theorem, so it's not critical. But if you're familiar with it, it's important. Okay, so now we have some basic understanding of what happens if you take up, again, the conclusion of that, all that we discussed is very simple. If you take a piece of plastic or some material, you roughen it, put it in any radiation, black body or not, you can always get the intensity enhancement up to 2n squared. Maybe a little more if you're willing to restrict angles. That's so far what we have gotten. So far so good. Now we're going to use it for light trapping, okay, to absorb more light. What does light trapping mean? This is what it means. So if you take a piece of transparent material, plastic, and if it's very flat, light comes in, it refracts, and it refracts out. Nothing happens to it, nothing is struck, that's all you get. You get a single pass. Okay? This was, I think, one of the first questions in the midterm. Now, of course, this is not very good because many semiconductors, like silicon, it's an indirect band gap semiconductor. It has very low absorption. If you only get one pass, the probability that the photons are absorbed is quite low. It won't work so good. You want to increase the number of passes to give it more chances of being absorbed. So a simple way to do it is put a mirror in the back so you get 2 passes. Okay? You can increase the complexity by putting some regular structure on top. So this is kind of a historical thing if you think about what happened in solar systems. We'll start putting those in just to randomize a little bit. There wasn't really a random structure like these pyramid structures. So you get a little bit more bouncing around. But then people started doing this random stuff. And you get all kinds of bounces. And then you can randomize both surfaces. You get even more bounces. And you can do all kinds of crazy stuff, designing these randomness very carefully. You can get more bounces as a function of sun traveling around, during the day. But that's the basic idea. You're allowed to bounce around inside the active material more and more times, so you can get absorbed.
Would that create more heat then?
So good question. Heat comes from what? Let's think about it. And we haven't talked about solar cells, so that it's hard. So you may not appreciate it.
Absorb.
So when photon is absorbed, many things can happen, right? Heat is just one of them. Of course, what we really want to happen is we really want to create current. We want to create an electron-hole pair, right? But you're absolutely right. When a photon is absorbed, lots of things can happen. You can create heat, you can create current. it can re-radiate. Yeah? Anything that absorbs will also re-radiate. All things can happen. But in a good solar cell, you want less heat and more current. In a good LED, you want less heat, more radiation. And very interestingly, about 5 years ago, there was an interesting paper by the same guy who wrote this paper. He said a good solar cell is also a good LED. And this was very interesting, and that was really the title of the paper. Very important insight. Means that what can absorb light well must also emit light well. And in a sense, it makes common sense because it has to agree with the second law of thermodynamics. Anything that absorbs well has to emit well. Anyway, it's an interesting paper in itself. So the question of heat is very important, but we'll come to that. Let's table that for the time being. It's not necessarily related to this. It is related to what happens after it's absorbed. Although I should also point out, you are correct in the sense that you can have heating that comes from this, if you're not a good reflector, right? Let's say you're 99% reflection efficiency. What happens to that 1%? Typically becomes heat. And if you're doing it thousands or millions of times, it can be significant, so you have to be careful. But one good thing is that usually these turn out to be heat sinks, so you can use aluminum frame or whatever. So it helps to cool down that material, which is always good. So all of these are important considerations. So in almost all solar cells today, wow, it's hard to see, but you kind of see it better. If you actually open up usually you can't see this because it's planarized with a protective coating, like silicon nitride. And I'm not talking about the glass. So if you take a solar cell, you can remove the glass. That's not hard. If you look at what's underneath it, it's actually a flat layer of silicon nitride. And if somehow, if you are able to remove the silicon nitride, you will see something like this. Yeah, something like this. So this is the silicon part. This is the texture I was talking about. It can be like this, it can be like that. Lots of they're created many different ways. We won't talk about it. But they're very common. I would say almost 100% of solar cells today. And probably those are electron microscope images, so it's pretty small. So why do we want light trapping? Of course, to enhance the absorption, but you could also enhance the absorption by simply making the silicon cells thicker, right? If I just make it infinitely thicker, I don't need so many passes. I can just absorb it, right?
The cost.
So the cost, yeah. Silicon is cheap, but even then it gets expensive. But other things, maybe you might want to make it flexible. Although there's not a huge market for this today, but it's a possibility. But you will learn in the lecture on the review solar cells that there is a fundamental reason why thinner solar cells are also better. It's because, we'll explain the very cartoon sense right now, but we'll look at it in more detail when we talk about the physics of solar cells. This is related to your question about the light absorption. So let's imagine you have a semiconductor where a photon came in, okay, got absorbed, and you create these electron hole pairs, right? Create these electron hole pairs, electron in the conduction band, in the hole in the valence band. And this will start moving, forming current. Now, as the electron hole pairs move in the semiconductor, again, lots of things can happen. This electron can very easily see another hole and annihilate itself, emitting light or emitting heat as excitrons. Okay, vibrations in the crystal. That's bad. Because you want these electron hole pairs to enter the battery to charge it, right? Or run the motor or whatever you're trying to do. But other things can happen before that happens. Okay? Or if you have defects in your crystals and things like that. Now, if you want to avoid all this or minimize the probability of all that happening, you can make your cells really, really thin. So the distance that these electron hole pairs have to travel can be very small. And you can increase the likelihood it will reach the ends. So now think about a very thin cell versus a very thick cell. If I have a electron hole pair here, it has to travel a long distance. Whereas if I have an electron hole pair here, it has to travel a short distance. Right? So it's an advantage. A higher probability I can get the electron hole pairs out. And that's a very fundamental problem.
So
Yes?
going thicker doesn't solve the problem at all. It makes it
It
worse.
depends on what you're trying to do. If you're willing to spend a lot of money, this could be a problem. You can solve this problem by making a very pure crystal with no defects.
Oh, I see.
So, and there is a big fundamental difference. So if you're NASA, for instance, you won't need to have solar panels on your Mars rover. You don't particularly care about money. And you want the efficiency, right? Your rover doesn't have much room, so you want to pack as much efficient cells as possible. Whereas if you're on a big solar farm, it's a complete opposite. It's a very different requirement. So there is a market for both. That's the answer. So that's what I mean by here. If you make a thin semiconductor, you can have a higher quality with fewer defects and less carrier recombination, which is the loss that I was talking about. We'll talk more about it later. So now we have to introduce absorption. So we haven't talked about absorption before, so let's introduce absorption. Very simple. So again, we are going to talk about the input light. The incident area comes into play because now we have to talk about power. So it is area times intensity gives you power. The T incident is the same as before, the probability of light transmits. Light will escape at the same rate as before, but you have a different area here, escape. We'll make them equal, but let's just make them different for now. Exactly the same expression as before. Okay. Now, absorption can happen many places. So let's imagine again a thin film. So light can come in, and the texture there, and refracting, right? So you can have absorption happening at the interface here. Some light could get absorbed. This is called edge recombination, absorption, and things like that. There's all kinds of terms for it, but it's imaginary. So at that interface, or it can also happen here, right? Any of these interfaces. It can also happen there. So we can compute the fraction of light as absorbed by doing this integral, where a reflection is the area that is reflected. It includes the top as well because it also reflects at the top, times the intensity inside, the same expression as before, except now we have a term eta, which is what we call the fractional absorption on the interface. The integral is the same. Again, remember, we only do it within the cone, which is where the reflection happens. So that's why it's no, this is for all the angles, right? Never mind. It's strange. I had to think about that, right? When we come back to that. Right, this integral right now is done in, what is there to 9 degrees. I thought you only need to do it. No, because some of it, it's the opposite. You need to do all the angles because you can have reflection at all the angles because of an L as well. Right? Keep that in mind. Yeah. So it's not necessarily directly related to total interreflection. Now, for total interreflection, we'll assume it's 100% reflection. There's no loss there. So it's okay. It's fine. Now, the other absorption can happen in the bulk. So in other words, when light is bouncing around in this material, some of it gets absorbed because it's silicon, right? It's band gap, like we just talked about. From photon is absorbed, electron hole pairs are created. We need to model that as well. And that can be modeled with this term here, alpha. Which is referred to as the absorption coefficient. So alpha times the intensity inside divided by 2 pi dv d omega, and we do the integral. dv is a volume, and we're looking at a tiny volume, and we integrate over all the volume of interest and all the solid angles of interest, which we can write as follows: alpha times L, which is the effective thickness of this layer, more or less this thickness. Interior intensity, area that's incident, times this angle center, which is the d omega converted into 2D angles. You end up with this expression here. 2 alpha L, I interior is. You can work out the math, it's not so important. We'll put it all together and try to draw some conclusion. So light in equals light out. So incident area times transmission times incident intensity, that's of course what's coming in, should be equal to what happened? That's weird. I didn't touch it. That is strange snap. Okay. Don't know why that happened. So on the right hand side we have the escape loss, absorption at the interfaces, absorption inside the bulk, three terms. Okay? It's that, and you can work it out, write all this. So that's the incident intensity related to all this stuff. Now, recall that our goal is to increase the absorption in the solar cell. The absorption itself, or how much power is absorbed, can be written as 2 alpha L, the factor 2 because of the reflection, is in I2. Remember, this is the same term we had here. Okay? That's the absorption in the bulk of the solar cell, which is what we're trying to utilize. Right? So this is what we are trying to increase, and you can get an expression for that. So the fraction of the incoming light, and this is what we are really interested in. Let's rewrite it. Fraction of incoming light that's absorbed in the bulk. In other words, how much is absorbed divided by how much came in. Okay, so you can say, okay, 50% is absorbed, 50% of whatever it is. So this is the important thing. And now we're going to make some assumptions to gain intuition from it. Okay. Now let's actually, we'll leave it here. So first of all, let's do some assumptions down here. Let's make all the areas the same, so I'll ignore the areas. Next, we're going to assume that the alpha is very small, weakly absorbing, which is always true for silicon. We're going to ignore that. Okay. Now, let's see, what do we end up with? So we have these two terms. Right? Actually, let's make this term. So at the top, what do we have? We have 2 alpha L times T incident divided by, I'm going to remove all the A, so this becomes T by escape. We have a 2n squared plus beta over 2. Okay? I cancelled out the A's. Is that okay? Right? Now also I'm going to make the assumption that this is very small. Let's get rid of it. What was that? That was just the absorption in the interfaces. Let's just say we have very nice interfaces, very low absorption. I'm also going to say that this and this are the same, which is, remember, has to do with the Fresnel losses. It is approximately symmetric, so it will be about the same. So what we end up with, and 2 cancel, no, the 2 doesn't cancel, sorry. So this 2n squared goes to the numerator, so we'll write that. Multiplied by what's here, alpha L. So we have 4n squared L comes up. Okay?
Did we not make the assumption that the alpha was really small?
Yes, but it's small relative to this, so we ignore this term. We ignore this term relative to this. We still keep it on the top. It's like saying, imagine I have a 1 on the top, and I have 1,000 plus 1. I'm ignoring this one. This is approximately equal to 1 over 1,000. Okay? Okay? Yeah? Okay. So we end up with this expression, which is here. So it's a weak absorption, so it is in there by gap semiconductors, alpha small. Let's assume eta small. This means fractional absorption due to imperfect reflections is very small, it's that case. Also, T bar escape is approximately 2 incident. So maximum absorption enhancement is 4n squared, L times alpha, but L times alpha is the standard, right? So actually, I should have removed L times alpha, sorry. Coming back here, why do I still have it? Let me think here. Sorry, yeah, correct, yeah, no, it's correct. So if I don't have anything, if I have one pass through my material, so let's imagine I have that material, light passes through once. I'm going to do it normal incident for the sake of argument. And this thickness is there, and this absorption is alpha. The amount, fractional amount of absorption I'll get is L times alpha. I don't do anything to it. So the increase in the absorption is 4n squared. 4n squared times L times. Okay? So that's maximum absorption. And that's a pretty substantial number, right? Number to n squared was roughly 9. 4n squared can be 40, almost 40. That's a pretty substantial increase. Right? It's crazy if you can actually get that. So, what does this mean? So, in the paper, they do some experiments, and the experiments are very simple, so it's useful to kind of understand what they do. There's a device called integrating sphere. All it does is it absorbs all the light that comes into it and measures and gives a reading, like a power reading. Okay? So the integrating sphere has an opening where you put a silicon wafer, okay? And there's a reflective surface behind the silicon wafer. And light's coming in from here. So there is another opening which is not shown that sends the light in. Let's ignore that for the time. So polished side faces the light, so it's flat facing the light, and there's a textured side at the bottom. Okay? Can be flat, real surface can be flat or textured. So you compare two situations. One, both surfaces are flat. Another situation, you have one surface is textured, one surface is flat. And then look how much is reflected back. Right? So let's think about this for a second. And the reflected light is measured by integrating sphere. So let me draw this so you can appreciate what this means. So in one situation, I have completely flat. Another situation, let's imagine a mirror in the back. And the other situation, I have something which is textured with a mirror in the back. And I'm measuring what came back, reflected back. Now, you tell me from your understanding so far which one will have more light reflected back. And you probably have to think and discuss, so hopefully you discuss with your neighbors. It's all related to what we talked about so far. So take a minute or so and think about it.
Question is the amount, because on both surfaces it becomes all the way around
How would you think about this problem, right? Considering,
yeah, there's pretty some
about the absorption, what you're
Yes.
kind of measuring is what's absorbed.
Exactly.
The rough edge
so let's say more. So what would you, okay, so you have the answer, but we'll talk about this. You tell me the answer, so what do you think? Which one will have more reflected light? First one. That's it. And the reason is this will absorb more. Correct. So, but let's think about the logic. So what's happening to the light? Light comes in, goes through to one of these, reflects back, and straight back. Here what's happening? Comes in, bounces around, might reflect, but bounces around a little bit more. So more chances of being absorbed, and some of it comes back. That's the logic. It's a very simple experiment, right?
But if we rough up the outside surface again, now
Yeah,
that rough
get more.
oxide surface gives us more reflection back too,
That's a
doesn't
good point, except it turns out we know from our analysis it will also enhance the light trapping part of it also.
So what, but there's a higher percentage that comes out from the initial.
Yeah,
but all the rest that goes in is more likely to stick.
Exactly. Yeah. You get more randomness. But what he's showing is that you don't need to do it. That's what it basically shows.
Well, you don't need to have the rough.
You don't need to. You need it's very, very easy to create the roughness in the light. One surface is enough. But if you have two, it will get even better. You'll get some extra reflection, but you'll get much more bouncing around and absorption that you will overwhelm that. It's a good question. It's a very simple experiment, no? And that's the result. So this is plotting backscattered light as a function of wavelength, so that's wavelength. This wavelength is important because this is where silicon absorbs. The band gap is above here. This is, wavelength is decreasing, energy is increasing of the photon. And the result is basically the percentage of light that's backscattered out. The top curve, the solid curve, is being measured with a flat surface. So lots of light is reflected out. Okay. And as you increase absorption with the texturing, this curve drops, as we know, less light is reflected. Of course, beyond the band gap, there's very little difference. Everything is basically absorbed. It's not so important, but this is really very
Everything is absorbed past the band gap.
when the energy is higher than the band gap. This we know. Yeah. It's not so critical for our discussion yet. We'll talk more about it. Generally speaking, people talk about light trapping, they almost always look near the band gap. Near the band gap, it's hard to absorb for most of the semiconductors like silicon. So you try to do some tricks to enhance the absorption. The dashed lines, the theory, so it matches, which is good. Okay, so the last topic we need to cover. Say that again?
It's better than theory, because the dotted line is theory.
Yeah,
Better than
maybe, yeah, but it depends on how you model it and so on. Yeah, it's close enough, let's say. Whoops. So we need to hurry because there's one last thing we want to talk about is a different implementation of light trapping. Is using little granules of silicon embedded in plexiglass. So PMMA is plexiglass, that we call plastic. Right? So here you have little balls of silicon. It is of course useless, right? You can't really use it for current because they are isolated and insulated, right? But let's imagine this is an experiment in absorption. In theory, if you make that polymer conductive or if you had a way to incorporate conduction between those granules, you could extract them. And, I think people work on this, for instance, in silver nanowires and things like that. So it's interesting. Yeah. But it's just to show what happens is that even though this silicon is a very small fraction of the total area, it can be like 10% or something like that, you can extract a lot more light just because of this factor of light trapping. The light that comes into the plastic can essentially bounce around and make its way to silicon, almost like a waveguide. So we'll see that. Silicon microspheres are embedded in the PMMA, which is polymetal metacrilates. It's a polymer plexiglass. Light is trapped in silicon, has a higher refractive index than PMMA, and it enhances the absorption. Okay, so very quickly, we can do the detailed balance calculation as well. Logically simple, right? Light from air going to PMMA plus silicon going into PMMA should match the light going from PMMA to air plus PMMA to silicon. Everything should balance and become an equilibrium. Write down the equations exactly the same as before, but now you have to be careful because there's three things there. One is air, two is silicon, three is PMMA. I won't go through it, but it's exactly the same as before. You can work it out. Work on all this stuff. Then we apply, so that's detailed balance in PMMA. We can do the same thing in silicon. Same thing, air to silicon plus PMMA to silicon should match silicon to air plus silicon to PMMA. So each component has to be internally equilibrium, right? Nothing is heating up or cooling down. You get a similar sort of expression. So we have two equations we can solve. Okay. Well, what are we solving for? We are solving for absorption inside silicon. So which is We haven't written down elements. Oh, no, we haven't written down it. No, it is related to this alpha L, but I haven't written down that yet. Actually, we didn't derive it. It's in the paper. I didn't put it in. But we can solve these two equations to calculate what is the intensity of light inside the silicon. Right? It has to be enhanced from what we know. And the expression comes out to be something like this. The refractive index of a silicon is 3.53. Refractive index of titanium is 1.5. This transmission, the Snell reflection, it's about 4%, so 96% is transmitted with a good anti-reflection coating. We'll talk about what this is later on. You get a transmission, the intensity inside the silicon of this expression. Okay. This alpha L is the important thing, the absorption. L is the thickness. Times 0.96 I1. This is I1 is the transmitted incident intensity, what comes in. 0.96 times I1. If you're within the band gap of silicon, alpha is small, so ignore that. You get this expression. It's approximately 22 squared times I1. Same as before, what we expect. And 2 is the refractive index. So pretty big impact here as well. And that's what the experiment results. With no silicon granules, 100% is reflected back. Remember, there's a mirror in the back. Plexiglass is transparent, so just glass. Once you add the silicon, you start absorbing. Makes sense, right? What reflects that? That's the last slide, so we'll stop here. So today, just to summarize, what we have thought about, it might be a little abstract, so I recommend you go, and I went through things a little fast. I recommend you at least skim the paper to get a feeling for it. The reason is we will use this